Afternoon. Welcome to lecture 22 on Riemannian Symmetric Space. Last lecture we have defined as very useful proposition. We have stated a useful proposition that let phi G2S be a smooth homomorphism. Put d phi is equal to d phi E, then d phi from G to Lie algebra d phi is the differential of phi at the identity. Then d phi is a Lie algebra homomorphism. And we have the following diagram is commutative. This so this diagram is very important, and it will be useful to us in. So this is the relation phi of exponential of x is equal to exponential of d pi x. So today we will talk about something called adjoint representation. It is a very important concept. So let G be a Lie group. So so for G belongs to G, we define IZ from G to G by IGH is equal to this GH G inverse. So, this H belongs to G. So this IG is a clearly a smooth map because this is a conjugation by G. Really, and this is really an automorphism of G. So IG is smooth isomorphism from G onto G. Now I'll so this is a notation we define. RG is really this DIG at the point E. Now since IG is a isomorphism from G to G onto G, this RG is a really a this RG will be a Lie algebra isomorphism. This is my picture. So this is my IG and this is my RG. So this RG will belong to where? This is belongs to automorphism of G, and that is subset of something like GLG. So where this automorphism of G, if you have recalled, this is so T belongs to GLG. So that Tx of y is equal to Tx for all x comma y belongs to G. So this is the thing, and from this thing you get that so Ig of exponential of x this is equal to exponential of RGX. So that will imply something G of exponential of x G inverse exponential of RGX. So we also check that. It is very easy to check that this I of G1 G2 really I of G1 composition I of G2, and if you take this thing d I G1 G2, so derivative at the point identity. So
what was the last line of the previous page? Can you just go back to the last line?
IG exponential of
x is exponential at gx. Okay, fine. Thank you.
So G of exponential x G is the inverse is equal to x. So IG1 G2 is equal to IG1 composition I G2. So this is real DI G1 at the point E, DI G2. If I take the derivative at the point identity, so this will give you odd of G1 G2. So this is really odd of G1 composition odd of G2. So that means odd. So this map odd from G to this GLG is a group homomorphism. And these are called representation. Thus defines a representation of G called as a adjoint representation. Okay, so it is
continuous, hence infinity.
continuity. I will say, sir. So if you will now you fix a basis B is equal to really B1, B2, Bn of G. Then if you fix this basis B, then so GLG you can identify it with GLNR. So therefore GLG is a Lie group. So yes, GLG is a Lie group with Lie algebra. Small, we write Lie algebra small GLG, and that is really endomorphism of. So it can be shown that this R from G to GLG is a smooth map. It's smooth. So this is a thing. So we have another thing. So let I define small r. This is really derivative of capital R at the point identity. Okay. So that will give you a diagram G to GLG. This is really R and small g, and this is really small r, and this is my exponential map, and this is my exponential. So from here actually you will get this thing. So your R of exponential of x, exponential of Rx. Now Rx is a element from GLG, so this is Rx belongs to really GLG. So that therefore this in the and we are in the matrix setup. Okay? This is a linear map. So this is same thing as e to the power Rx. Now it can be shown that this Rxy is really Lie bracket of xy. So this is the thing. Now one example in the let us see what happens in the matrix Lie group setup. So example, so let G subset of GLNC be a matrix Lie group. So we have this situation that G subset of GLNC, and this is really MNC. So by definition, this G is a embedded submanifold of GLNC. Submanifold. And similarly, GLNC is a embedded submanifold of MNC, because I am borrowing the topology there from MNC. This implies G is a subset of really MNC. It's Lie algebra, where G is the Lie algebra of G. Now let G belongs to G. Here Ig will be from G to G is given by, so Ig of A is equal to really GA G inverse. Now observe Ig extends to a linear map. Linear map from MNC to MNC. So given by this Ig of X is equal to Gx G inverse. And this G is a submanifold of MNC. Thus Rg is equal to dig at the point identity, and since this is linear map, so this is really Ig. Hence if X belongs to G, this really Rg of X is equal to Rg is equal to Ig of X. So this is really Gx. Now in this setup, so in this setup, so hard x of y is really xy. This is really matrixmal to xy minus y. So now this is all about adjoint representation. Let us let us go back to symmetric space. Okay. So so let G be a, so let us the definition. Let G be a Lie group with a Riemannian metric Q on it. Then Q is said to be, so this is really I have left invariant. This is thing if LG belongs to really Ig for every G belongs to be right invariant. This if Rg means right translation, this belongs to isometric group for every G belongs to G. C is bi-invariant. If both LG and Rg belongs to Ig, so for every G belongs to G. So the thing is, if J is a Lie group, then Q is said to be left invariant. If left translations, that belongs to the isometric group, and right invariant if right translation belongs to the isometric group, and bi-invariant if both left and right translation belongs to isometric. Okay, so now so let M be a smooth manifold. So you know that there are you can put always a Riemannian metric on a given smooth manifold, and you can put infinitely many Riemannian metric on a given smooth manifold. You have to use something called partition of infinity. So one can put infinitely many Riemannian metric metric on a given smooth, in a given on the manifold A. Now I want to really ask the same question for Lie group, but I want the metric should respect the group structure in certain way. Hence I am asking that whether the Riemannian metric which I will put on the Lie group G, that is always that is whether left invariant or right invariant or bi-invariant. That is the question I am interested in now. So so let us here discuss. Discussion. So let G be a for Riemannian manifold. I have to start with a connected Lie group, right? Because Riemannian manifolds by definition is connected. Let G be a connected Lie group. So claim G always admits a left invariant Riemannian matrix Q on it. So this is very easy. So let this is choose any inner product on the tangent space on G, which is really easy, and I want to define a Riemannian metric using this thing. I have to use the left translation. So define QG from TGG plus TGG. Okay, so to R by actually let us use the place this actually. So QG this QG and I have to take this UV. So this is really, so I will so UV belongs to TGG. Okay, so this is really DLG inverse G Q GB. So see the thing is so you take this thing is okay, so let us take this map from G to G and you take this LG inverse that will map G to E and DLG inverse will map from TGG to TEG, and this is what I am doing. So since this the DLG inverse G, this belongs to TEG, this is well defined, and so since this LG inverse is smooth, therefore this is a indeed a Riemannian metric on Q. Q is a clearly Q is a Riemannian metric on G. Observe one thing, you should really this is G inverse and this point is G inverse G. These two things you have to really remember. Okay, so claim this is a left invariant Riemannian pool. So to show that let so H belongs to this G and UB belongs to THG. So what you have to show? You have to show Q of if you want to show that this is left invariant, so Q of LG at H, so DLG at H U DLG HB. You have to show this thing as a QH UV. Okay. If you want to show that this metric is left invariant, so let us show that. So this is Q GH and DLG HU. So DLGH. So this is really, by definition, this is really DLGH inverse. Okay. GH DLGHU DLGH inverse GH DLGHB. So now I have to really calculate this thing. So let us use a fresh space. So this is really DL. This is GH inverse GH. GH composition, what DLGH. DLGH. So this is same thing, a D of LGH inverse composition LG at the point H, a DL H inverse G inverse composition LG H, and this is the thing L of A dot B is really LA composition LB. Use that fact here. So this is really D of L H inverse G inverse. Sorry, LG inverse composition LG H, and this LG inverse LG composition, that is identity. So this is really, so D LH inverse H. So this thing is you're getting the DLH inverse H. So let us write that. So this is really DLH inverse H U. So DLH inverse H. So now this is actually the definition of, this is really QHU. This is really QHU. So this is. So that implies this implies this is really LG belongs to isometric, and this is for this has we have shown for energy of G, since so G is arbitrary, therefore the Q is a left invariant Riemannian metric constant. Metric constant. So Tapendo, is it clear?
Yes, Mother. So exactly
So,
what material did you use? Only connected.
Exactly. What are you
hypothesis
saying?
we assumed on G?
G is only connectedly group.
To prove this theorem.
So
Connectedly
just
group.
you have putting a inner product on the tangent space at the identity, then you use the left translation to produce a left invariant Riemannian metric. That is the idea, okay? Natural idea, and that is what you are really doing. So remark one, by using that similar argument really one can produce a right invariant Riemannian metric Q and V. Okay, so the second thing is observed that second remark. This really, so this inner product is completely arbitrary on this TEZ. Okay, so we, in particular, in principle, we can get infinitely many left invariant Riemannian structures on a the Lie group G. So since, and that this is arbitrary, okay, choice of This is on. See, then we can left invariant Riemannian metric on. Pritam, are you able to hear me? Hello?
Yes, yes.
Okay, since choice of this is arbitrary on G, we'll get. Now, third thing is very interesting. See, the thing is to any Riemannian manifold, actually, you really can associate something called a Riemannian measure. Okay, since you are really utilizing this left translation, so to any Riemannian manifold, you can associate something called Riemannian measure. But since this Riemannian metric is left invariant, so you expect that the Riemannian measure is left invariant. Okay, and that is true, and therefore it gives rise to a left hand measure. So since third remark is the associated Riemannian measure corresponding to the left invariant Riemannian metric is left invariant, hence a left hand measure answer. Now the next question is we want to investigate when do you get a bi-invariant Riemannian metric on G? So
Muna, I have a question here.
yes, sir.
These left arm measures are unique up to constants, right?
Yes, sir.
On the other hand, left invariant Riemannian metric, the way you have produced, is completely arbitrary of the tangent space of the identity. After that, it has been
Yes.
transported using the left translation.
Yes, sir.
So, this arbitrariness of that inner product, is it hidden in those constants?
Arbitrariness of inner product
On the identity's tangent space, is that getting reflected in those constants?
on those constant. Yes. Yes, sir. That's right.
So this metric is unique up to a constant. Is that sir was saying?
This metric is not really unit. See, the thing is, Haar measure is unique, right?
Uh,
No, see,
So
yeah. So
what I understand is, if you have two Riemannian metric, they differ by a determinant, no? Is that so?
Riemannian metric,
Uh,
Riemannian metric or
no,
yeah.
Riemann,
See the thing. See the thing is actually I didn't want it to write that. So that will be something like GIJ. If you like take. Okay, so what is the Riemannian measure in this set? Okay, so let me clarify those things. It will. Okay. So let us little bit clarify this thing. See, the thing is, from here actually, the way we have defined, the thing is, if you look at the set of really left invariant
metrics.
Riemannian metric, Riemannian metric. So this will really is a one-to-one correspondence to positive
Yeah.
definitely bilinear forms or inner products on. I should have read that is the inner product, but forms on G. Okay, so this is the thing, and what is the Riemannian measure? So if you really try this Gij, dx g, you can write this thing like this gij dxi tensor diz. If you, I am talking about a say coordinate chart, okay, for a moment. And in this setup also this is ij. So you take this determinant of this matrix gij, and then you take the square root modulus and dx1, dx2, dx.
Correct.
This is the Riemannian measure.
Yeah.
Okay, so this will be mu. Okay, so this is the Riemannian measure. So this is the Riemannian. Now the thing is, actually one gets a Haar measure, but Haar measure really Haar measure unique up to this scalar multiple, right? Okay. So suppose you fix a Haar measure on G mu naught belongs to say mu naught fixed Haar measure on G. Then if mu is another Haar measure on G, Haar measure, then this mu is equal to some c times mu naught, and this c actually is this depends on the inner product on G. Product on this G, which SKR pointed. Okay. So these are very appendo. Is it clear?
Yes, ma'am.
So there are certain things actually in in this Lie group setup. Actually, you get usually Haar measure by this thing, or shop called you have to produce a top order volume form like that. Okay, so now let us question. So that GBA connected Lie group, is it possible to really to get a bi-invariant Riemannian metric? This question is little interesting. And answer is no, and so counter example is really whereas cell to R. Okay, I will see in later that why this is cell to R is really the thing. Now proposition. So let GBA connected Lie group. So then the following are equivalent. So G admits a bi-invariant Riemannian metric on it. So let us say this is a really a. This is equivalent to what there exists an RG invariant inner product on G. Look at the statement very carefully. GBA connected Lie group. Then the following are equivalent. G admits a bi-invariant Riemannian metric on it. Is equivalent to fact that there exists an RG invariant inner product on G. So let us prove this thing. So proof this is A implies B. Suppose Q is a bi-invariant Riemannian metric on G. G. Now this QE is a inner product on tangent space G, and you expect that the QE is an RG invariant inner product. So clearly QE is an inner product of. So you have to show that this QE is RG invariant. So let QB belongs to G, then QE the RGU, so RGB. So this is really what QE RG is really, you know that. Okay, so IG from G to G is really IG of H. So really GH G inverse. So IG you can write that is really LG composition RG inverse. So if I take this DIG at the point identity, so DLG, okay, so let us, so this is equal to DLG and DRG inverse, and identity, this is G inverse. So that means RG, you will get what? This will get DLG G inverse, composition DRG inverse. So this is the thing we have to use. So QE in place of RG, you write this thing. This is the equation I am using. So DLG G inverse DRG inverse. So yeah, okay. So this is becoming messy. Okay. So this is Q D L inverse D R G inverse E U, and so this is the thing. So now you use this thing that Q is left invariant. So that will give you this QG Q G inverse DRG inverse EU DRG inverse E. I do something wrong here somehow. QG inverse. Sorry, okay, just wait. I did some. DRG inverse E. Yeah, this is okay. That is perfectly fine. So this is really QE UB by this okay right invariance of RG inverse. See, you can write this. Let us write it almost. This is really RG inverse E DRG inverse E U DRG inverse E V, and this I am using this right invariant of Q, that is the Q of UV. So therefore I get this thing that QE is RG invariant. And so you get this QE is an RG invariant inner product. Now conversely, this B implies A. So let this thing be an RG. These are easy things actually, but you writing is maybe might be messy. Be an urgent band inner product on G. So define this UG UV. This is the same thing which we have used in the previous way. DLG inverse G UV DLG inverse G. This is really U comma V belongs to TGG. So this is really okay. So we have already seen that. U is a left invariant Riemannian matrix. Matrix on G. I have to only show that this is really right invariant. So let this H belongs to G. So the Q and UV belongs to THG. So this is really Q of. I have to only show that this is right in the Q of RGH, and so D of RG HU, D of RG HB. So this is really what? So this is equal to Q of RGH. So HG DRGHU DRGHB. So this is by definition what? Is by definition this is D of L HG inverse HG DRG HU DL HG inverse at the point HG and DRG HB. So let us calculate this thing in the next page. So it's DL HG inverse HG composition what DRGH. So this is same thing as D L HG inverse composition RG H. Okay. Now what is this L of HG inverse composition RG of say M? You calculate this thing. So this is really L of HG inverse and RGM, then that means MG. So and this is really G inverse H inverse MG. So this is same thing as what? So this is I G inverse L H inverse M. So this I write here D. So therefore I get what? L H G inverse composition RG is same thing as I of G inverse composition LH. So I put that here DIG inverse composition LH inverse at the point H. So this is DIG inverse and DLH inverse H, and this H inverse is identity. So this is really RG inverse. So DLH inverse H. So I put that thing. Okay, remember this term RG inverse DLH inverse H. So I have to put here. So this is equal to really odd G inverse DLH inverse H. This is really odd G inverse DLH inverse H. Now this DLH inverse this you will take H2 identity, so this belongs to really G. This belongs to G, and you have assumed that this is really this inner product is a G invariant, so that will give you so DLH inverse HU. Now DLH inverse HB. So that means this is definition QH QB. So that means RG star Q is equal to really Q. Thus RG belongs to RG. Hence Q is right invariant. Hence Q is right invariant. Therefore Q is a bi-invariant. Hence Q is bi-invariant because Q is first right invariant. Riemannian metric. Therefore Q is bi-invariant. So this is the thing. So okay. So what did you prove? That you proved that in a connected Lie group, G admits a bi-invariant metric on it if and only there exists an RG invariant inner product on G. So now one proposition. Let G be a connected Lie group so that RG is compact. RG or G is compact, then G possesses a bi-invariant Riemannian metric on it. This is a really, I think this is easy because if so this is you just average, you have to just let G prime is equal to really RG, and this is compact. Let this be any inner product be any inner product on this tangent space. So you define this thing for U D belongs to G. You define this thing new inner product U B not really. This is really G U G B D G, and this is G prime where G D G is the normalized harmonizer of normalize is not needed, but I want to normalized harmonizer of G prime. Left okay. So this actually left and right in this case are same, but
By G dot U, do you mean at G of U?
yes. No, actually, yeah, that is the action. G is of the form some RH G dot that is really RJ Actually, I am not saying. Actually, this is a tricky question. I am not saying this is something like G RG U RG B DG. I am not saying right. G is an element of G prime. Is it clear, sir?
Yes.
If you will define this UV0 like G is RG, sorry, RGU RG.
Yes, I understand why you were avoiding it. Yes.
No, I am saying I am not saying for you. Actually, I'm saying for other. Okay. So this is the normalized measure of G prime. So clearly this new inner product is an RG invariant. So, inner product on this where inner product on G. Therefore, by previous proposition, I have. Oh, I left some gap here. Okay, by previous proposition, this um, G admits a bi-invariant Riemannian metric, Riemannian structure on it. Now this, if G is compact, then RG is compact. So therefore, rest this thing is this is also clear. So rest part of the proposition is also clear. Is also clear. So, okay. So this is the thing, and so remark. I just wanted to give two remarks. So first remark is so let G be a connector Lero. So that it admits it has a bi-invariant Riemannian metric. Okay, on it, then G has to be necessarily unimodular. G is necessarily unimodular because it is the Riemannian measure has to be left invariant and right invariant. So then G is necessarily unimodular. But however, this converse is not true because SL2R is that example. The converse is not true. So this is really a counter example. So counter example is SL2R. So this is, and if you look at this modular function, see the thing is we have proved that if G has a really this Lie algebra has a RG invariant Riemannian product, RG invariant inner product, then it has a bi-invariant Riemannian metric. So RG is coming somewhere. So the thing is, if you in the case of connected Lie group, you can calculate this modular function explicitly. So let so if so let G be a connected Lie group. So it can be shown that the modular function delta G is really Modular function delta z is called determinant of RG. Determinant of RG, and you take them. This is the thing. Now, if RG is compact, then this determinant of RG has to be necessarily 1. Then in that case, also from here, also you are getting if RG is compact, then the group is unimodular. So now this is really
You are basically saying that the left translation and right translation basically differs by energy. No?
yes. That is actually is coming. Actually, so this so let let G is compact. This implies really. Okay, before that, let me give a question here. Okay. Investigate. Okay, so I am putting it exercise. With the condition on G. So that the bi-invariant Riemannian matrix on G is unique up to scalar multiple. Okay, so in this case you can get some uniqueness. Hint is something your source lemma, and something you have to just think about it. Okay, so let G be a compact connected group. So that implies RG is compact. So now the question is, can you give an example where RG is compact but this G is non-compact? However, the converse is not true. It's not true. So for instance, first example I am giving that. So let G be any connected abelian group. This may not be compact. For instance, G is equal to really S1 cross S1 cross S1, and this some R to the power n. So this is really, so take times. So this G is abelian. Okay, G is a non-compact abelian degree. So what you do, this Ig from G to G is really what? Ig of H is equal to really G H G inverse. But since this is abelian, this is called H. Okay. So Rg is called Dig at the point identity. So since this Ig is the identity map, so Dig is equal to identity. Therefore, Rg you will get in this case is called identity, and which is clearly compact. This is clearly compact, but G is non-compact. So second example is we take this thing. So second example. So let G is equal to really K cross Rn, where K is a compact group. Then if you look at this Rg, this is really Rk. this is isomer. This is isomorphism. This is really isomorphism. This is RK and RRM. And this is really RK, and this RRM is really identity, right? Because RM is a abelian Lie group, so this is really this identity. So this is isomorphic to this RK, and this is compact. So clearly, these are non-compact, but but RD is compact. So now the thing is, RD is compact. Okay, so now I want to state a theorem. This is a very important theorem. Let G be a connected Lie group with a bi-invariant Riemannian metric Q18. Then the exponential map from Lie algebra to this group Lie group G is a this map is coincides with Riemannian exponential map. This Riemannian exponential, okay, with the Riemannian map for this value. The exponential part of that to G, and moreover the geodesics emanating from G belongs to G are precisely of this form. The form G exponential of Tx. This T is from minus infinity to infinity for some x belongs to G. And also this exponential map from G to the surrogate. So this is really we are not going to prove this thing, but this is a good result to know. It is proof is in there. You can proof you can find Helene Helgason. So this is the thing that let G be a connected Lie group with a bi-invariant Riemannian metric Q18. Then exponential map coincides with the Riemannian exponential map, and moreover the geodesic emanating from G belongs to G are precisely of the form G exponential of Tx, and also exponential map G from G to G is surjective. So this actually answers the question which was asked by Rajesh Priya once in one of the previous lecture. Okay. So corollary, and this you can get a corollary that so. Corollary this so if let GB so that this RG so that G or RG is compact, Then this exponential map from Lie algebra to is surjective. This is really. So now the thing is exercise, so that this exponential map from SL2R to really SL2R is not on two. You can take this an exercise. This is an easier exercise, not on two. So from the above exercise, so there above from previous theorem and above exercise, it is clear that SL2R doesn't admit a bi-invariant Riemannian matrix. Riemannian matrix. So SL2R doesn't have a bi-invariant. So now we want to really prove a very important theorem that if G is a compact Lie group, or then that is a Riemannian symmetric space. So, okay, theorem. So let G be a connected Lie group which admits a okay, that it admits a invariant Q on it. Then G is a Riemannian symmetric space. So this is a very important example and really proof. See, the thing is, I have told you that that if you know a given a Riemannian manifold, if you know the geodesics of that Riemannian manifold, it is very easy to prove that that manifold is a Riemannian symmetric space. Okay. So and we will use that thing. Okay. So first observe that since this LG belongs to isometry of G. For each G belongs to G. Therefore, this implies, because I am assuming that this G is a admits a bi-invariant Riemannian matrix, so this implies IG acts transitively on G. So hence we have proved that proposition that if some isometric group acts transitively on the manifold M, then if to show that is a Riemannian symmetric space, it is sufficient to produce a geodesic inversion at a given point. Okay. Hence it is sufficient to hence so by proposition, actually that proposition is in page 311. This note. It is sufficient to produce a geodesic inversion at identity. So at identity. Okay. Now I have you really know that this geodesics to passing through this identity are of the form exponential of Tx. Now suppose this is exponential of Tx. So this SE of exponential of Tx, since this is a geodesic inversion, this will have to be exponential of minus Tx. So this has to be. Okay, we know that because this exponential Tx is the geodesic inversion, and this is precisely this map So define SEG is really G inverse. This is precisely this map. SEG is equal to G inverse. Okay. So we are just using that previous theorem. Okay, we are just getting a clue how to define this isometry, and we are defining this SEG by G inverse, but we are not really using that previous theorem. So what I am saying that using that previous theorem, we are just getting a clue how to define this geodesic inversion at the point identity, but we are not really using that theorem. That you have to understand. Okay. So define SEG is equal to G inverse. So clearly, so this is SEG is equal to G inverse. So clearly, this SE is equal to E. That's clear. Now, since SE exponential of TS is equal to exponential of minus TX, and that this implies if you differentiate that, so dSEX is equal to really minus x. Hence, and this is really exponential. So I am using this fact that if you, so what is dFB? I am using this fact dFB B is equal to d by dt, t is equal to 0, f composition gamma t. Okay, where gamma t is a curve with gamma prime 0 is equal to 1. So I am using this. So dSEX is equal to minus x. So hence this dSE is equal to minus identity. I will finish this proof. Okay. So clearly, SE from G to G is a diffeomorphism, because so I have to really only show that this SE is an isometry. So to show that, let UV belongs to TGG. Now, so this Q of SEG, DSEG, U, DSEGB. So this is really what? Q of G inverse. So DSEGU, DSE. So now this is really, since this is a left invariant matrix, so Q of DL QE of, so DL G and G inverse D of SE GU, so DLG G inverse DSE G. So I have to calculate this thing. So let us use this thing. So this is really what? DLG G inverse DSEG. So DLG G inverse DSEG. So this is really D of LG composition SE. Now what is D LG composition SE? This LG composition SE is really G. Okay. So LG SEH is called as inverse. This is really GH inverse. So that you can write this really HG inverse inverse. So this is SE and this is RG inverse composition H. So this implies LG composition SE. We are really getting SE composition RG inverse. So this is really okay. So this is really D of LG composition SE composition RG inverse G. So this is D SE D RG inverse G, and this DSE E, but DSE is equal to minus of minus of identity. So yeah, we have seen that DACAC is equal to minus identity. I am using that TF as the inverse. So hence I get what? This is equal to, oh god. Okay, I am writing after this. Okay, so these are just only calculation. Okay, so you understand that what is. So I am writing this. This is equal to really. This is equal to QE. Okay, so this is really minus of DRG inverse G. Okay, so U and minus of dr inverse GB. So you can really minus minus, you can take this will come out, so that will be QV drg inverse GU, so drg inverse GB, and you use this okay, you use this thing that this is a right so this metric is right gene variant, so this is really QZ, okay, UV. So Q, as Q is right, Q is right invariant. So that means this says that SC belongs to IG. Okay. Hence, so we have this SC, hence SE is a geodesic inversion. The geodesic inversion at E. Therefore, G is a RSS. So in final corollary. So this example is going to be very important later. So let G be a connected Lie group, so that RG or G is compact, then G is a RSS, Riemannian Symmetric Space. So any compact connected Lie group is a Riemannian Symmetric Space, and we have little bit generalization of that result. So now the thing is, we will so later on in the next lecture we will we will define some topology on the isometric group, and we will see that IMA is a Lie group. I will not prove that, I will just state that, and then we will move towards the Lie theoretic characterization of symmetric space. Okay, so with this I would like to stop, and if there is any question I will be happy to answer it. Tapendo, Riju.
No question from me.
No question.
So let us start then. Santanu? Or let us start.